Hello, my name is Tristan Hodgins, and I made a little video here to explain the concepts behind the attack lab for ECN 224. Um, this video isn't going to explain exactly how you're supposed to do the lab. It won't show any of the code, really, or what you need to inject in order to get your program to run. However, it is going to explain the concepts, particularly behind phase one of the lab. So first, we need to understand the stack. As you know, the stack is a place for your program to store its local memory. Let's run through the execution of this simple program I have right here. It's mostly in pseudocode, but that'll be sufficient for our understanding. So first, when main is called, sometimes it's going to create a stack frame. And a stack frame is just a section of memory where main is going to store local variables. Oftentimes this will be strings, or if a function has so many variables, integers, that they can't be stored in registers, it'll also create a stack frame. I don't know, the compiler decides what it needs to do, but it might create a stack frame. And when you were doing the bomb lab, you might have seen a line of code like this: add OX18 to RSP. That's the creation of the stack frame, where main is allocating that many bytes. I believe that's actually 24 bytes to have its stack frame. So the main function will do stuff. It'll reference its stack frame, it'll play around with its registers, you know what it does. And then when we get to when it calls real function, what it's going to do is it's going to put a return address onto the stack. And the reason it does this is that when real function is called, it's going to execute. And then once real function is done executing, the code needs to know where to return to. It needs to know what line of code it needs to continue its execution. So it's going to return the memory address of the line of assembly code that's right after real function. Um, because remember, all code is stored in memory as well. So once real function is called, it might also create a stack frame. So it'll do the same thing where it adds onto the stack. It has its stack frame for doing its own thing. It's going to do stuff. And now when real function hits its return statement, it's going to deallocate its stack frame. And that'll be similar to line, or that'll be the reverse of the line for allocating stack frame. It'll just subtract some amount of bytes from the stack. It's important to note that when a stack frame is deallocated, it's not actually deleted, but your computer says that it's fine to be overwritten. So if main were to call another function after real function that also created a stack frame, it would also go right here. It would just overwrite what real function did. But for simplicity, I'm just going to show that it was deleted. When the return statement is also hit, real function is going to look at the return statement that was previously put on the stack, and it's going to put that return statement into RIP, which you might remember is a register that points to the next instruction that is to be read. So in other words, return is a fancy way of saying pop RIP. Um, once the once the return statement is popped, it's going to go back to main. Main's going to do its stuff, and likewise, when it hits its return statement, it's going to clear its stack frame. So now let's apply this knowledge to the lab. Here's the pseudocode for what C targets basically looks like. We have a main function that's going to set up the lab. It's going to call a function called getBuff, and if getBuff returns successfully, it's going to send you a message that says, hey, you didn't actually do what you were supposed to do. The program ran successfully. So you, as an evil hacker in this lab, failed the lab. And it's going to return 0. We have this function called touch1. It's not actually called by main at any point, as you can see. But you want it to be called because touch1 has code that'll send a message to the server that says, hey, this student successfully ran this code, you get points for phase 1, and then it'll kill your program. And now let's talk about getBuff. So what getBuff does is it's going to set up an input string or a stack frame, and it's going to call a function called gets. Now gets is a C library function that should not be used anymore. In the 1900s, gets was commonly used, but it's not it's not memory safe, meaning that you can override portions of your memory if you give in too long of an input string. And we'll see that here in just a second. So if we go through a normal execution of this lab, meaning that you didn't inject any code, what's going to happen is you'll get to main. Let's say main doesn't create its own stack frame. So it's going to call getBuff, it's going to put its return address onto the stack. GetBuff will execute, it'll create its stack frame, and it will call gets. And gets is just going to load in whatever input you put into the program into the stack frame that getBuff created. And then getBuff doesn't actually do anything with its string. It just will return, and then it'll go back to main and tell you failed and you did not pass the lab. However, if we rewind a little bit back to where we set up the input string and called gets, if you put in an input string that is longer than the buffer that was allocated in getBuff, in other words, you put in more bytes than the getBuff stack frame allocated for, your input will begin overriding other parts of the stack, including that return address that's supposed to point you back to main. So what will happen now is everything will get deallocated, the stack frame will go on as normal, and it'll try to read the return statement, but remember, the return statement was overwritten by your input. If your input doesn't have a valid memory address right here, it'll just crash your program because it doesn't know what's going on. However, if you're clever and the last 8 bytes of your input are the memory address for touch 1, the return address, or when you get the ret command in assembly, it'll go to touch 1 instead of to main, and it will do the sending of the successful message stuff, and it'll upload to the server that you succeeded and everything is good and dandy. Future or subsequent phases of the lab will have you put in input into registers because touch 2 requires a cookie to be passed in, so does touch 3, and then phase 4 is a little bit different as well, but you can read those instructions on the website, and of course it can always come into TA hours. I wish you luck on the attack lab.